Hello, I'm Hanrui. I'll tell you something about our paper in EC'23, efficiently solving turn-taking stochastic games with extensive form correlation. It's a joint work with Cheng and Vincent Conitzer. So first, let me give you a very quick overview of the results. The focus of this paper is on two-player turn-taking stochastic games. So that means games and dynamic environments represented in the graph form, which is the more succinct representation of such games. So in the paper, we design algorithms for two things. First, stochastic extensor form correlated equilibria, or SEFCE in polynomial time. And second, optimal extensor form correlated equilibria, or optimal EFCE up to epsilon in time polylog 1 over epsilon. So I'll explain what these terms mean very soon. The key challenge in designing these algorithms is that these equilibria are generally history dependent, which means the flat representation of these equilibria are exponentially large. So we can't easily compute the flat representation. We have to find a way to encode these games in a more succinct way. So, okay, let's get started. First, let me review the landscape of equilibrium computation so far. So normal form games, which are games in static environments, we understand very well. We know that natural equilibrium, these equilibria are hard to compute in normal form games. But on the other hand, we have efficient algorithms for equilibrium concepts with correlation or commitment. So by that, I mean correlated equilibrium or Stackelberg equilibrium. So that's the case of normal form games. What about dynamic environments? These games, it turns out, they are more tricky than normal form games. So what do we know? We know that computing optimal or Stackelberg equilibrium is hard, even with normal form correlation. So that's the kind of correlation that we consider in normal form games, which makes equilibrium computation easy in normal form games. So such correlation doesn't make equilibrium computation easy in stochastic or extensor form games, which are games in dynamic environments. So what we do know about tractability is that tractability in dynamic games often requires extensive form correlation. So let me explain. The difference between normal form correlation and extensive form correlation is normal form correlation is a one-shot thing. So on the left, you see one example for normal form correlation. So the mediator, which is the one who tells the players which action they should play in the game in the equilibrium. So with normal form correlation, the mediator says, I'll flip coins now at the beginning of the game and tell you what actions you should take in every possible situation you may encounter in the entire play of the game. So the mediator says something like, you should play action A1 in state 1, action A2 in state 2, action AN in state N. So the entire plan for a play of the game. And now the players can go play the game according to the plans. So it's a one-shot revelation of the entire recommendation of actions. So extensive form correlation is different because it's like a gradual process of revealing more information to the players. So with extensive form correlation, the mediator says something like, I'll flip coins now at the beginning of the game and tell you what actions to take only before you need to take it, actually. So an action and recommended action is reviewed right before the player has to take the action. So what the mediator does throughout the play of a game is something like, when the players reach state 1, the mediator says, well, we are in state 1, now you should play action A1. And then the player takes the action, the game evolves, right? And now we are in state 2. Mediator says, well, we are in state 2 now, so you should play action A2, and so on and so forth. So it's a gradual process of giving the players more and more information about the equilibrium strategies. And what is a extensive form correlated equilibrium? So here's an example. Now, at the beginning of the game, the mediator says, here's how I plan to generate recommendations. It's like a huge distribution of recommendations, but you won't see the actual realized recommendations just yet at the beginning of the game. So the game begins. We are now in state 1. The mediator generates the first action for Alice. Mediator tells Alice to play action 1. So because this is a extensive form correlated equilibrium, so Alice rationally believes that it's in her best interest to follow the recommendation and play action A1. So the game proceeds. We are in state 2. Mediator tells Bob to play action A2. And again, because this is an equilibrium, Bob is willing to play action A2 because it's the best course of action for Bob. And the game proceeds. We are in state 3. So mediator tells Alice to play action A3. Now, there's something tricky that happened, right? So Alice now actually regrets playing A1 earlier. So Alice was willing to play A1 because she wasn't able to see the later recommendation, which is A3. And now Alice actually sees A3, and she does regret playing A1 earlier. But still, Alice is willing to follow the recommendation from this point onward because we are already in state 3, and because we are playing according to a correlated equilibrium, Alice is rationally motivated to keep following the recommendations, and so on and so forth. So that's the concept of extensive form correlated equilibrium. So with that concept in mind, we have more possibility results. Right? So with extensive form correlation, we have efficient algorithms for Stackelberg or optimal equilibria when there's no chance move, which means nature doesn't flip coins. We have algorithms for Stackelberg equilibria in perfect information games. And we also have an algorithm for optimal equilibria when the chance moves are public, and many other algorithms for other variants of these games. So the catch here is that all these algorithms only work for extensive form games, or you could say tree form games. So which is different from the kind of games that we look at in this paper. So in this paper, we focus on stochastic games or graph form games. So the first question you're going to ask is that really such a big deal, right? So let's try to understand the difference between the two kind of games. So the difference between game trees and game graphs is illustrated by this simple example of NIM. So the game of NIM is where initially there are K matches on the table, and the two players, Alice and Bob, they take turns removing matches. Every time one of the two players can remove either 1 or 2 matches, and they take turns removing matches. The one player who removes the last match on the table wins the game. So for example, what you see on the right is one segment of a play of the game. So at some point of the game, we have 3 matches left. Alice removes 1 match, and then we have 2 matches left, and Bob can remove 2 matches and win, and the game ends there. So how do we represent this game? Well, of course, you can see the game is zero-sum, and it's fairly easy to solve, which is not a point here. So we care mostly about the representation of the game, which is how we show the difference between game trees and game graphs. So what about game trees? Game trees are the canonical representation of extensive form games, which is the focus of earlier algorithms in dynamic equilibrium computation. So the game tree of NIM looks like this. So the root is where we have K matches left, and Alice is the next player to move. And then Alice can choose to take either 1 match or 2 matches. If Alice takes one match, we go to the left subtree where we have k minus 1 matches left, and it's Bob's turn to move. So from there on, Bob can choose to remove one match or two matches. If Bob chooses to remove one match, we go to the left subtree where we have k minus 2 matches left, and it's again Alice's turn to move, and so on and so forth. So we can generate the entire game tree in this fashion. So something interesting about this game tree is that these two nodes in red, they are exactly the same. So the question, the obvious question when you have these identical subtrees is why don't we merge them, right? So we can merge them. If we do merge them, we get the game graph, which is the canonical representation of stochastic games. So the game graph of them looks like this. So initially we are at this node. We have k matches, and Alex moves next. And then Alex can remove either one match or two matches. So if Alice removes one match, we go to this node. K minus 1 matches left, Bob's turn. And Bob can remove one match or two matches, right? So let's say Bob actually removes two matches. Then we go to this node, k minus 3 matches left, Alice's turn. So one important quantity that we really care about here is the size of the representation of the game, right? So in the game tree, the size of the representation or number of nodes is exponential in k, which is the initial number of matches. But in the game graph, the size of the game is linear in k, and that is much smaller. So this is precisely why we care about stochastic games or graph form games, because a algorithm that runs in polynomial time in the size of a game graph can be much more efficient than an algorithm that runs in polynomial time in the size of the game tree of the same game, because there can be a huge gap between the size of the graph and the size of the tree. Okay, so before actually explaining the algorithm, let me try to explain why it's hard to design an algorithm for equilibrium computation in these games. So the main challenge is history dependency, and I'll show that in this example. So initially, we are in the leftmost state where nature flips coins and generates randomness. With probability 0.5, we go to the top node, and this probability 0.5, we go to the bottom node. So both nodes belong to Bob, so Bob moves next. In the top node, Bob can choose either this action, moving to the right, which terminates the game, gives Alice minus 100 in reward, and gives Bob 0. Or Bob can choose to move diagonally to this node, which gives Alice utility 1 and Bob utility 0. So Bob doesn't really care, but Alice wants Bob to take the diagonal action. In the bottom node, Bob can again do two things, right? Bob can either take the diagonal action and terminate the game, which gives Alice utility minus 100 and Bob utility 0, or Bob can choose to move right, which gives Alice utility 1 and Bob utility minus 1. So Bob is facing essentially the same decision in the two nodes with only one difference. If Bob chooses to keep playing the game, which is this action and this action, then the utility for Bob is different in the two states. So in the top state, it's 0, and in bottom state, it's minus 1. And then if we are in this node, then it's again Alice's turn to move. Alice can do two things. Alice can either take this action, which gives Alice utility 1 and Bob utility 0, or Alice can take this action, which gives Alice utility 0 and Bob utility 1. So what does the optimal, the Stackelberg equilibrium look like when Alice is the leader? So if we don't have history dependency, that is, if we require the strategy to be history independent, then Alice's optimal commitment looks like the yellow strategy. So Alice can only take this action, the yellow action here, which gives Bob utility 1. And the reason for that is if Alice doesn't give Bob utility 1, then if by chance Bob ends up in this node, the bottom node, then Bob would choose to end the game immediately because then Bob gets utility 0. And alternatively, if Bob chose to continue the game, then what he gets is utility -1 plus 0, which is smaller than 0. So anyway, you can check. This is the best course of action for Alice if Alice is the leader in this game. Now, instead, if we allow history dependency, then Alice can do something much more clever. So what Alice can do is Alice picks the red action if Bob came from the top state here. And Alice picks the sort of bluish action if Bob came from the state in the bottom, this state. So if Alice does this, then the utility, the expected utility of Alice will be 1.5, which is better than 1. So this is, in fact, the Stackelberg equilibrium with extensive form correlation in this game. So you can see it depends on the history of where Bob came from. So that's the tricky part of this problem. So what that tells us is that the flat representation of these equilibria are exponentially large. So we can't just compute the flat representation. We need to encode them in some succinct way. So now we're ready for an overview of the algorithm. The high-level idea is that we know the flat representation is huge, so we don't compute that. Instead, we look at the Pareto frontier curves that sort of encode the equilibrium. So these curves, the curve for state action pair S and A, is the optimal way to trade off between the two players' utilities after playing action A in state S, subject to equilibrium conditions in the future, roughly speaking. So if we have these curves, then the Stackelberg or optimal equilibrium corresponds precisely to some optimal point on a certain curve. And these are what the curves look like. So the algorithm, very roughly speaking, does recursive evaluations of these curves, which is possible because we can do binary searching over the direction of the evaluations. And that combined with some memorization technique gives us a efficient algorithm for computing extensive form correlated equilibria. And there are more details in the paper, of course. Now, for future directions, in this paper, we have been looking at turn-taking stochastic games. So natural question, what about simultaneous move stochastic games, which are more general than turn-taking stochastic games? We don't know anything about them, no algorithms, no hardness. Also in this paper, we have a algorithm for optimal EFC up to machine precision in time log 1 over epsilon. So what about exact computation of optimal EFCE in turn-taking stochastic games? We don't know anything about that. So maybe there are hardness results, maybe there's efficient algorithms, we don't know. So that's all. Thank you for your attention. I can take questions offline.